Good morning. It's January 2nd, and this is your daily brief in science. Here's everything you need to know. Human metapneumovirus, or HMPV, is increasingly being identified among children, showing symptoms similar to those of the common cold and COVID-19, including cough, fever, nasal congestion, and wheezing. Severe cases can escalate to bronchitis or pneumonia, particularly impacting vulnerable populations such as infants, the elderly, and individuals with existing lung conditions like asthma, COPD, or emphysema. Recent data from China highlights a notable surge in respiratory infections, particularly HMPV, among children under 14 during the week of December 16 to 22, 2024. State broadcaster CCTV reports that this winter's respiratory infections are primarily attributed to influenza, with HMPV also contributing to the rising numbers. The virus spreads through respiratory droplets from coughing or sneezing and can also be transmitted through close contact and contaminated surfaces, with an incubation period of 3 to 5 days. Currently, there is no vaccine available for HMPV, and preventive measures include maintaining good hand hygiene, avoiding contact with infected individuals, and disinfecting surfaces. The CDC recommends additional preventive measures such as wearing masks in crowded settings, maintaining social distance, frequent hand washing, and ensuring proper ventilation in indoor spaces. Management of HMPV focuses on symptomatic relief, as there is no specific antiviral treatment. Over-the-counter medications may be utilized for those with chronic respiratory conditions. In the United States, HMPV typically circulates from winter to spring, accounting for 5% to 10% of hospitalizations in children, with up to 16% of these cases leading to serious complications like pneumonia. While mild cases often resolve within a few days, severe instances can result in more serious respiratory conditions. In response to the increase in HMPV cases, China's National Disease Control and Prevention Administration has implemented protocols for laboratory reporting and case verification, and is piloting a monitoring system for pneumonia of unknown origin as respiratory disease cases are expected to continue rising throughout the winter. A new method for identifying infectious variants of viruses and bacteria could change the landscape of disease surveillance. This groundbreaking study, led by Dr. Nomi Lafranc from the University of Cambridge, was published in the journal Nature on January 2, 2025. The innovative technique has been tested on various pathogens, including Bordetella pertussis and Mycobacterium tuberculosis. During a whooping cough outbreak, it revealed 3 previously undetected variants of Bordetella pertussis, as well as 2 antibiotic-resistant variants of Mycobacterium tuberculosis that are currently spreading. By detecting these antibiotic-resistant variants, the method aids in treatment decisions for infected individuals, which helps limit the spread of diseases. This approach constructs family trees for pathogens, automatically identifying new variants based on genetic changes and transmissibility, effectively streamlining the classification process. Utilizing genetic sequencing data, this method enhances the understanding of genetic changes contributing to the emergence of new variants. It improves surveillance capabilities, which is critical as current systems primarily focus on COVID-19 and influenza. Researchers highlight the potential of this method to enhance global infectious disease surveillance and inform effective public health responses. It is applicable to a wide range of pathogens and requires only a small number of samples, making it particularly useful in resource-limited settings. The ability to monitor pathogens in real time from human samples allows for the quick identification of vaccine-evading strains. Insights from this research could transform governmental responses to infectious disease outbreaks worldwide, addressing the ongoing evolution of pathogens underscored by the emergence of new strains during the COVID-19 pandemic. A new study from researchers at King's College London is shedding light on the intersection of machine learning and biological aging. Published in the journal Science Advances, this research explores how AI models can be utilized to create metabolomic aging clocks using plasma metabolite data from the UK Biobank. The study evaluated various artificial intelligence algorithms to determine the most effective method for predicting biological age based on human blood samples. By comparing these algorithms, the researchers aim to enhance the accuracy of metabolomic aging clocks, specifically utilizing nuclear magnetic resonance spectroscopy data. Data from over 225,000 participants, aged between 37 and 73 years, was analyzed, focusing on 168 metabolites found in their blood plasma. Among the tested algorithms, the cubist regression model proved to be the most accurate, achieving a mean absolute error of just 5.31 years in predicting biological age. The research introduced a concept called mileage, which measures the difference between predicted biological age and chronological age. Significant gaps in this measurement indicate accelerated aging, which was found to correlate with poorer health outcomes, including chronic illnesses, and a frailty index score disparity of up to 18 years. Moreover, the study revealed that a 1-year increase in mileage delta was associated with a 4% rise in all-cause mortality risk, emphasizing the serious implications of accelerated aging. The researchers concluded that metabolomic aging clocks could be effective predictors of biological aging and health outcomes, paving the way for future clinical applications. This research highlights the potential of aging clocks as biomarkers that may be tailored for studies on lifespan and health span extension. Additionally, the analysis confirmed non-linear relationships between metabolites and age, suggesting that statistical corrections may be necessary to improve prediction accuracy. Future research may focus on developing aging clocks based on tissues and cells to further enhance our understanding of the aging process. A recent study from the University of Arizona has unveiled a surprising capability in patients with artificial hearts: the potential to regenerate heart muscle. This groundbreaking research indicates that these patients regenerate muscle cells at a rate over 6 times higher than those with healthy hearts, shedding light on the heart's intrinsic regenerative abilities. Co-led by Dr. Hesham Sadek, the study published in the journal Circulation proposes that artificial hearts create a resting state for heart muscle, which may facilitate recovery. Dr. Sadek drew an interesting parallel between muscle recovery seen in sports injuries and the potential for artificial hearts to enhance heart muscle regeneration. He emphasized that the heart muscle's inability to rest could limit its regenerative capabilities, a concept he has been investigating since 2011. The research aims to understand why only about 25% of artificial heart patients exhibit muscle regeneration and seeks ways to improve this response across all patients. Heart failure affects approximately 7 million adults in the U.S. annually and accounts for 14% of all deaths, with current treatments primarily involving heart transplants or devices like left ventricular assist devices, also known as LVADs. This study is part of a larger initiative to advance heart failure treatments and could significantly change the management of heart disease, especially considering that artificial hearts are already established medical devices. The research utilized tissue samples from patients with artificial hearts, collaborating with experts from the University of Utah and the Karolinska Institute in Sweden and Germany. The implications of these findings could pave the way for innovative treatments in the fight against heart failure. Researchers are making strides in creating a comprehensive global map of human genealogy, aiming to enhance our understanding of genetic diversity across the human population. Dr. Yan Wang, an evolutionary geneticist, has led a team that constructed a large family tree for humanity, which models genetic relationships among individuals. This family tree allows researchers to visualize the ancestry of specific genomic regions, tracing genetic segments back to their ancestors. The study employs a tree sequence concept, which traces genetic variation through time and identifies common ancestors within evolutionary trees. These findings are supported by geographical data that help infer the locations of common ancestors and recapitulate significant events in human evolution, such as the migration out of Africa. Notably, the earliest identified ancestors are traced back to modern-day Sudan, indicating a much older origin for certain human lineages than previously understood. Over the past 2 decades, genetic research has advanced significantly, driven by an increase in genomic data collection from hundreds of thousands of individuals, including both contemporary and ancient populations. This research combined data from 8 databases, totaling 3,609 genome sequences from 215 populations, including genomes that date back over 1 million years. However, the research faced 2 major challenges: integrating genome sequences from various databases and developing algorithms capable of processing large datasets. To tackle these issues, a new method developed at the University of Oxford's Big Data Institute aims to integrate data from multiple sources and scale to millions of genome sequences. The research team plans to continuously integrate new genetic data to enhance the genealogical map's comprehensiveness, with the potential to accommodate millions more genomes. Additionally, the methodology developed in this study is applicable to other organisms, including medical genetics, helping to distinguish genuine genetic associations from spurious connections. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.